As we look to the night sky, we are often captivated by the fleeting brilliance of comets, celestial wanderers that trace arcs of ice and dust across the heavens. Among the many comets that have graced our skies in recent years, two stand out for the stark contrast in their fates. See 2025 R2’s SWAN, which met a dramatic end as it ventured too close to the Sun, and 3I Atlas, an interstellar traveler that defied expectations and survived its passage through the inner solar system. While both comets offer valuable insights into the nature of these enigmatic objects, the disintegration of C2025 R2 holds particular significance. Unlike 3I Atlas, which continues its journey outward, R2's fate serves as a powerful reminder of the delicate balance that governs the survival of comets. Its story is not just one of destruction, but of the forces that shape the evolution of these icy bodies and the broader dynamics of the solar system. To understand why C2025 R2's disintegration matters more than 3I Atlas's survival, we must first consider the fundamental nature of comets. These celestial objects are remnants from the early solar system, composed primarily of frozen volatiles such as water, methane, and carbon dioxide, along with rocky material. When a comet ventures close to the Sun, the intense heat causes its ices to sublimate, forming a glowing coma and a sweeping tail of gas and dust. Most comets survive this process, gradually losing mass with each orbit, but some are not so fortunate. If a comet's nucleus is structurally weak, or if it ventures too close to the Sun, the resulting pressure and temperature changes can lead to catastrophic fragmentation. The disintegration of C2025 R2 offers scientists a unique opportunity to study this process in real time, providing crucial data on how comets behave under extreme conditions. The contrast with 3I Atlas is equally fascinating. As the third confirmed interstellar object to visit our solar system, 3I Atlas represents a rare glimpse into the chemistry and composition of objects formed in distant star systems. Its survival, despite its close approach to the Sun, raises intriguing questions about its structural integrity and the nature of interstellar comets. However, while 3I Atlas' survival is certainly remarkable, it does not provide the same level of insight into the mechanisms of cometary disintegration. Instead, it highlights the resilience of certain comets, reinforcing the idea that not all icy bodies are doomed to vanish after a single encounter with the Sun. In this way, the disintegration of C2025 R2 offers a more profound lesson, one that speaks to the fragility of comets and the delicate balance that determines their fate. By examining the final days of C2025 R2 and comparing them to the endurance of 3I Atlas, we can gain a deeper understanding of the forces that govern the evolution of comets. This exploration will take us through the intricate science behind these celestial phenomena, revealing the delicate interplay between a comet's composition, its trajectory, and the immense forces at play in the solar system. Along the way, we will uncover the broader implications of these events, from the formation of comets to the mysteries of interstellar objects. Ultimately, the disintegration of C2025 R2 is more than just a tale of cosmic demise. It is a testament to the ever-changing nature of the universe and the lessons hidden within the fleeting beauty of a passing comet. Comets are among the most fragile objects in the solar system, and their survival depends on a delicate balance between internal structure and external forces. At their core, comets are composed of a mixture of frozen volatiles, primarily water ice, carbon dioxide, methane, and ammonia, along with silicate dust and organic compounds. These materials are held together in a loosely bound nucleus, which lacks the rigid structure of rocky planets or asteroids. When a comet approaches the Sun, the intense heat causes the ices to sublimate directly from solid to gas, releasing jets of material that form the glowing coma and the characteristic tail. This process, known as outgassing, is essential to a comet's evolution, but it also places immense stress on the nucleus. If the internal structure of the comet is not strong enough to withstand the resulting expansion and pressure, it may begin to fragment or even disintegrate entirely. C2025 R2 SWAN provides a prime example of this process. Discovered by amateur astronomer Vladimir Bizugli, using images from the Solar and Heliospheric Observatory's SOHO SWAN instrument, the comet was initially observed with an apparent magnitude of 7.4, indicating a relatively bright object with a tail stretching over 2 degrees in length. Over the following weeks, it continued to brighten, peaking at magnitude 6.2 on 16 September 2025, making it visible to observers with binoculars. However, the rapid brightening was not a sign of stability. It was a harbinger of impending disintegration. By the end of September, the comet had faded significantly, and by 22 April 2025, its nucleus had completely disappeared, leaving behind only a diffuse dust cloud. The disintegration of C2025 R2 followed a familiar pattern seen in other comets that venture too close to the Sun. The intense solar radiation and tidal forces exerted on the nucleus caused the outer layers to sublimate, leading to a chain reaction that weakened the internal structure. Eventually, the comet fractured, and its fragments dispersed, unable to reform due to the lack of cohesive strength in the remaining material. The disintegration of C2025 R2 is particularly significant because it occurred under extreme conditions. The comet reached perihelion, the point in its orbit closest to the Sun, on 12 September 2025 at a distance of 0.5 AU, 75 million kilometers, placing it well within the orbit of Mercury. At this proximity, the Sun's gravitational pull exerts tidal stresses strong enough to tear apart loosely bound cometary nuclei. Additionally, the intense solar radiation causes rapid sublimation of the comet's ices, creating volatile jets that can destabilize the nucleus and contribute to fragmentation. The fact that C2025 R2 disintegrated despite its relatively large size, initial estimates suggested a nucleus of at least a few kilometers in diameter, highlights the vulnerability of even moderately sized comets when subjected to such extreme forces. The event underscores the importance of understanding the structural integrity of cometary nuclei and how they respond to the harsh environment of the inner solar system. In contrast, 3I Atlas demonstrated remarkable resilience despite its own perilous journey through the Sun's domain. Discovered by the Asteroid Terrestrial Impact Last Alert System, ATLAS, on 1 July 2025, the interstellar comet was initially observed at an apparent magnitude of 18, making it invisible to the naked eye. However, as it approached the Sun, it brightened significantly, with observations confirming the presence of a coma and a faint tail. By mid-July, the comet was already showing signs of activity, with spectroscopic analyses revealing the presence of water ice, carbon dioxide, and even traces of cyanide gas. Unlike C2025 R2, 3I Atlas did not experience a sudden and complete disintegration. Instead, it maintained its structural integrity as it passed through perihelion on 29 October 2025, at a distance of 1.36 AU, 20-30 million kilometers, a location just beyond the orbit of Earth. Despite the intense heating and solar radiation, the comet remained intact, continuing its journey through the solar system before eventually escaping into interstellar space. The survival of 3I Atlas raises intriguing questions about the nature of interstellar comets and their ability to withstand the Sun's influence. As the third confirmed interstellar object to visit the solar system, following 1I Oumuamua and 2I Borisov, 3I Atlas offers a rare opportunity to study the composition and behavior of objects originating from outside our planetary neighborhood. Unlike C2025 R2, which was a native solar system comet, 3I Atlas traveled through space for billions of years before encountering our Sun. Its survival suggests that it possesses a more robust structure, possibly due to a higher concentration of refractory materials, substances resistant to high temperatures, that help maintain its cohesion despite the intense solar radiation. Additionally, its hyperbolic trajectory, which brought it into the solar system at a velocity of 58 kilometers per second, 36 miles per second, indicates that it was not captured by the Sun's gravity, but instead passed through on a one-way journey. This distinction is crucial, as it confirms that 3I Atlas is not a member of the Oort cloud or any other solar system reservoir, but rather an object that originated from a distant star system. What sets 3I Atlas apart from C2025 R2 is not just its survival, but also the wealth of information it provided to scientists. Observations from the Hubble Space Telescope and the James Webb Space Telescope revealed that 3I Atlas is unusually rich in carbon dioxide, and contains a small amount of water ice, water vapor, carbon monoxide, and carbonyl sulfide. The presence of cyanide gas and atomic nickel vapor further distinguishes it from typical solar system comets, suggesting that it may have formed in a different chemical environment. These findings challenge existing models of comet formation and raise new questions about the diversity of interstellar objects. Unlike the fragmented remains of C2025 R2, which offered insights into the mechanics of cometary disintegration, 3I Atlas provides a glimpse into the chemical composition of objects from other star systems, expanding our understanding of the building blocks of the cosmos. The contrasting fates of C2025 R2 and 3I Atlas highlight the wide range of behaviors exhibited by Comet. While both objects were subject to the same fundamental forces, solar radiation, gravitational tides, and outgassing, their responses were vastly different. One disintegrated under the pressure, while the other endured and continued its journey. These differences underscore the complexity of cometary evolution and the factors that determine whether a comet survives its passage through the inner solar system. By studying these two cases in detail, scientists can refine their models of cometary behavior, improve predictions of future cometary activity, and gain a deeper appreciation for the dynamic nature of our cosmic neighborhood. The contrasting fates of C2025 R2 and 3I Atlas offer more than just a glimpse into the mechanics of cometary behavior. They also provide valuable insights into the broader processes that shape the evolution of the solar system and the nature of interstellar objects. Comets are among the most ancient bodies in our cosmic neighborhood, remnants from the early stages of planetary formation. Their survival or destruction during close encounters with the Sun can inform us about the composition and structural integrity of these primordial objects, shedding light on the conditions under which they formed. The disintegration of C2025 R2, for instance, reveals how loosely bound cometary nuclei can be, highlighting the vulnerability of these bodies when subjected to extreme thermal and gravitational forces. In contrast, the survival of 3I Atlas suggests that some comets possess a more resilient structure, potentially due to a higher concentration of refractory materials that resist sublimation and fragmentation. These observations contribute to our understanding of the diverse nature of comets and the factors that determine their longevity. Beyond their immediate physical characteristics, comets also serve as cosmic messengers, carrying with them the chemical signatures of their origins. The survival of 3I Atlas, in particular, presents a unique opportunity to study the composition of an interstellar object in unprecedented detail. Unlike C2025 R2, which disintegrated and left behind only a diffuse dust cloud, 3I Atlas remained intact long enough for astronomers to conduct extensive spectroscopic analyses. These observations revealed that the comet is unusually rich in carbon dioxide and contains a small amount of water ice, water vapor, carbon monoxide, and carbonyl sulfide. The presence of cyanide gas and atomic nickel vapor further distinguishes it from typical solar system comets, suggesting that it may have formed in a different chemical environment. These findings challenge existing models of comet formation and raise new questions about the diversity of interstellar objects. If 3I Atlas originated from a distant star system, its composition could provide clues about the conditions present in that region of the galaxy, offering a rare glimpse into the chemical makeup of other planetary systems. One of the most intriguing aspects of 3I Atlas is its extraordinary speed, 58 kilometers per second, 36 miles per second, relative to the Sun, which is significantly faster than the previous interstellar visitors, 1I Oumuamua and 2I Borisov. This hyperbolic excess velocity suggests that 3I Atlas was not captured by the Sun's gravity, but instead passed through the solar system on a one-way journey. The trajectory of the comet also places it among the most unusual interstellar objects observed to date, as it followed a retrograde and highly inclined orbit relative to the ecliptic plane. This deviation from the typical orbital patterns of solar system objects implies that 3I Atlas may have originated from a different region of the galaxy. Perhaps the thick disk, a population of older stars with lower metallicity and a different dynamical history compared to the thin disk from which most interstellar objects are believed to originate. If this hypothesis is correct, 3I Atlas could represent a new class of interstellar comets, distinct from those previously discovered, and may indicate that our current understanding of the distribution and motion of interstellar objects is incomplete. The survival of 3I Atlas also has important implications for the study of long-term cometary evolution. Many comets that originate in the distant reaches of the solar system, such as the Oort cloud, are expected to undergo multiple passes through the inner solar system before disintegrating or being ejected into interstellar space. However, the fact that 3I Atlas remained intact despite its close approach to the Sun challenges assumptions about the fragility of cometary nuclei. If interstellar comets can survive such encounters, it raises the possibility that some of these objects may persist for extended periods, potentially influencing the dynamics of the outer solar system. Additionally, the chemical composition of 3I Atlas suggests that interstellar comets may differ significantly from their solar system counterparts, which could have implications for theories of comet formation and the exchange of materials between planetary systems. Understanding these differences is crucial for refining models of planetary formation and determining whether comets from other star systems could have played a role in delivering essential organic molecules to early Earth. The disintegration of C2025 R2, on the other hand, provides a valuable case study in the mechanics of cometary fragmentation. The comet's rapid brightening and subsequent disintegration offer insights into how loosely bound cometary nuclei respond to the intense heat and tidal forces exerted by the Sun. The fact that C2025 R2 broke apart, despite its relatively large size, initial estimates suggested a nucleus of at least a few kilometers in diameter, suggests that some comets may be inherently unstable, even if they appear to be structurally sound from a distance. This observation supports the idea that many comets may be transient phenomena, capable of surviving only a limited number of close approaches to the Sun before disintegrating completely. The study of such events is essential for improving predictive models of cometary behavior and for assessing the potential hazards posed by comets that may come dangerously close to Earth in the future. Furthermore, the contrasting fates of these two comets highlight the importance of observational data in refining our understanding of cometary behavior. The discovery of C2025 R2 through the Solar and Heliospheric Observatory's SWAN instrument demonstrates the power of space-based telescopes in detecting and tracking comets, especially those that originate from the inner solar system. Similarly, the early detection of 3I Atlas by the Atlas survey underscores the value of ground-based surveys in identifying interstellar objects before they reach their closest approach to the Sun. These observations not only expand our knowledge of cometary dynamics, but also emphasize the need for continued investment in both space-based and ground-based observatories to detect and study these elusive objects. Ultimately, the stories of C2025 R2 and 3I Atlas illustrate the dynamic and unpredictable nature of the universe. While one comet met a dramatic end, the other defied expectations and continued its journey through the cosmos. These events remind us that the solar system is not a static environment, but a constantly evolving realm, where objects from the depths of space can shape our understanding of the cosmos. Whether through the fleeting brilliance of a disintegrating comet or the enduring presence of an interstellar traveler, each celestial visitor offers a unique window into the mysteries of the universe, inviting us to explore, question, and marvel at the vastness of space. The stories of C2025 R2 and 3I Atlas remind us that the universe is a place of constant change, where even the most ancient objects can meet their end in a blaze of brilliance or endure against all odds. These comets, born from the remnants of distant star systems and shaped by the forces of the cosmos, serve as fleeting messengers from the past, carrying with them secrets about the formation of planets, the evolution of solar systems, and the vast interconnectedness of the universe. Their journeys, whether ending in disintegration or continuing on toward the unknown, invite us to contemplate our own place in this grand cosmic narrative. As we gaze up at the night sky, we are reminded that we are not alone in the universe, nor are we separate from its unfolding story. The same forces that shape comets, gravity, radiation, and the relentless passage of time also influence the evolution of stars, planets, and even life itself. Just as C2025 R2 succumbed to the Sun's pull, and 3I Atlas emerge from the darkness of interstellar space, so too are we part of a continuous cycle of creation and transformation. The elements that make up our bodies, the air we breathe, and the very world we inhabit were forged in the hearts of dying stars, scattered across the cosmos, and gathered over billions of years to form the conditions necessary for life. In this way, we are not merely observers of the universe. We are its participants, woven into the same fabric that gives rise to comets, stars, and galaxies. Yet, for all our scientific advancements, the universe still holds mysteries that defy easy explanation. The disintegration of C-2025 R2 offers a glimpse into the fragility of celestial objects, while the survival of 3I Atlas challenges our assumptions about the resilience of interstellar comet. Each observation, each discovery, adds another piece to the puzzle of how the cosmos works, but also reveals how much we still have to learn. The study of comets is not just about understanding these icy wanderers, it is about understanding ourselves. Every time we peer into the depths of space, we are looking back in time, searching for clues about the origins of everything we know. Perhaps the greatest lesson these comets teach us is the importance of curiosity. The same spirit that drives scientists to study the fate of C-2025 R2 and the journey of 3I Atlas is the same spirit that has propelled human exploration for centuries. From the earliest stargazers to the modern astronomers who use cutting-edge technology to probe the universe, our desire to understand the cosmos has never wavered, and as we continue to explore, we are reminded that the universe is not a fixed, static entity. It is a living, breathing expanse of infinite possibilities. In the fleeting beauty of a comet's tail, or the silent passage of an interstellar traveler, we find a reflection of our own existence, a brief moment in the grand timeline of the cosmos, yet one filled with meaning, wonder, and the endless pursuit of knowledge.